Hi class, we just finished up a discussion on the physical agents of microbial control. Let's move on now and spend some time talking about the chemical agents of microbial control. Our chemical agents are going to be inherently different than our physical agents. They are going to rely on the interactions between atoms and molecules. These chemical agents can occur in liquid, gaseous, or solid states, and they can range from the low-level disinfectants and antiseptics to high-level sterilants and preservatives. In aqueous solutions, we are going to always have our chemical of choice dissolved in water for the solvent. A tincture, unlike an aqueous solution, is going to be a water-alcohol mixture. So when working with a tincture, it's water plus alcohol dissolving our chemical of choice. In an aqueous solution, it is going to be just water dissolving our chemical of choice. When we select a chemical for our disinfectant, we want it to work rapidly. We want it to work quickly, even if it's in very low concentrations. We also want it to be soluble in water and or alcohol and have long-term stability. We don't want it to break down and have a short shelf life. We don't want it to constantly buy more of it if we don't use it all right away. And then finally, we want it to be broad spectrum. We want it to work across a wide variety of kinds of microorganisms: fungi, protozoa, helminthes, bacteria, viruses, but we don't want it to be toxic to human animals and tissues. We also want it to be able to penetrate deeply into inanimate surfaces so that we can have a sustained, cumulative, or persistent action. So we want to be able to dissolve and go and saturate our inanimate objects. And then finally, we want it to be able to be effective even when exposed to lots of organic matter. We also want to make sure that it doesn't stain anything. We don't want it to change the colors of our clothing or our skin or our solids. We don't want it to corrode anything. We also want it to be sanitary, and we also want to remove unnecessary or foul odors. And we also want it to be very affordable and cheap and easy to find. In other words, we can't find it. No chemical completely fulfills all of these requirements. A couple come close though. Hydrogen peroxide and glutaraldehyde approach the ideal, but they don't meet all of those categories or ideals. When we look at a germicide, a chemical designed to kill germs, we evaluate it in terms of how effective it is at destroying the microbes in both medical and dental settings. High-level germicides need to be able to kill the endospore and would need to be able to be used as a sterilant. They need to be used to sterilize something. Intermediate level germicides are not going to be used as sterilants. They are not able to kill those bacterial endospores, but they will be able to kill fungal and non-bacterial spores. So a fungal spore, for example, can be killed by that intermediate level germicide. And then low-level germicides are only going to eliminate vegetative cells and a few select viruses, particularly enveloped viruses. When we look at our germicidal agents, the nature of the microorganism being treated is going to affect the activity of the chemicals. Other things that affect the activity of the chemicals of our germicidal agent include what kind of material that we're treating, or the degree of contamination, what is the concentration or what is the population size of our microorganism, or how long we expose that microorganism to the chemical, and then finally, what is the concentration of the chemical that we're exposing the microorganism to. High concentrated bleach, generally speaking, is more effective than dilute bleach at killing microorganisms. When we are looking at strength and concentration, we are typically going to need to define some terms and have some standardized terms that we can use to measure the strength or concentrations. A dilution is going to occur whenever we take a small amount of a concentrated liquid chemical and we mix it with a larger volume of solvent to achieve the ideal concentration or the specific ratio that we're looking for. Two common units of concentration that we use or ways to measure concentration that occur in healthcare and in microbiology settings are parts per million and percent solutions. Parts per million are used for concentration or chemicals that are effective at very dilute concentrations. Things of this nature are typically going to be bleach or iodine tinctures. For example, if we had a 3 part per million solution, that 3 part per million solution is going to be equivalent to a 0.0003% concentration. So because it's a pain in the butt to write a decimal point and all those zeros, we use parts per million. For solutions or chemicals that need to be at relatively high concentrations, we use percent solution to measure the concentration. And this is typically going to be measured out by weight or volume or both. Typically weight or volume is used. So the weight of the solvent is going to be divided by the weight of the solution to give us our percent solution. So we can look at a 6% solution. That's a fairly standard concentration of percent solution. 6% solution is equivalent to 60,000 parts per million. So you can go in between or interconvert parts per million and percent solutions, but generally speaking, if you have something in percent concentration, you want to keep it in percent concentration, and vice versa. If it's in parts per million, you typically want to keep it in parts per million. In very rare situations, you need to interconvert between those two units. So let's talk about the length of exposure. Most chemical compounds are going to need an adequate amount of time to form the chemical reactions that will kill the microorganisms that they're trying to destroy. The big limiting factor in most situations is going to be the cell envelope, the cell wall, the cytoplasmic membrane, and the slime capsule and glycocalyx. Getting the chemicals past that cellular envelope to the cytoplasm of the cell takes time. It takes a while for that diffusion to occur. And then finally, the composition of the material that's being treated also influences how long it takes to disinfect it. Smooth solid surfaces can be disinfected very quickly, but surfaces that have lots of pores or pockets or areas for microbes to hide in, so to speak, take a longer amount of time to be disinfected. If there's a lot of excess organic matter, that excess organic matter can deactivate or hinder penetration of the germicidal chemicals. And then finally, when we're trying to sterilize a piece of surgical equipment or something that must be completely sterilized, so we need to kill all the vegetative cells and all the endospores. During that sterilization process, you first need to clean it, generally speaking, with soap and water. And then after you've cleaned it with soap and water, then you expose it to the sterilizing chemical. And the reason you clean it with soap and water beforehand is because you want to remove that excess organic material that could potentially hinder penetration of the sterilant or the germicidal chemical. So let's look at times for chemical destructions of specific microorganisms and specific disinfecting agents. If we're using chlorine, which is typically going to be in the form of bleach or sodium hypochlorite, bleach at a 50 part per million concentration takes about 50 seconds to kill a Mycobacterium tuberculosis bacterium. If we have it at a 0.1 parts per million, it can kill a protozoal cyst in 150 minutes. And if we have a hep A virus at 3 parts per million, it takes 30 minutes to kill it. So what I want you to look at here is if we use bleach to disinfect something, it takes, generally speaking, 30 to 50 minutes. We're looking at typically a half hour to an hour for our time periods here. That 50 seconds is kind of the exception here. If we're working with ethyl alcohol to kill a wide variety of bacteria, we're looking at a period of minutes to kill the bacteria at a 70% concentration of ethyl alcohol. If we're working with hydrogen peroxide at 3% concentration, we're looking at seconds to kill our microorganisms. If we're looking with quat, like a quaternary ammonium compound, at low concentrations, it takes a period of minutes, tens of minutes to kill our microorganisms. And then ethylene oxide gas will take a wide time frame. It could be as short as 2 to 4 minutes or as long as 25 hours, depending on the kind of microorganisms that we're killing here. So the big trend I want to get you to take from this is different chemical compounds at different concentrations take differing amounts of times to kill different kinds of bacteria and microorganisms. Generally speaking, most individuals like to err on the side of caution. Commonly, you'll see overnight chlorine baths at elevated concentrations, like a 50 part per million or 100 part per million concentration, and you'll let the instrument or the solid material soak overnight for 10 to 12 hours to disinfect it, because it's easier to err on the side of caution. So if we look at bleach, it is a halogen disinfectant. Both chlorine and iodine are in group 17 on the periodic table. They are halogens. So they have 7 valence electrons and are very aggressively seeking that one additional valence electron. These halogens are capable of destroying both bacteria vegetative and endospore bacteria, depending on the concentration and the length of exposure. If we look at hydrogen peroxide is going to kill bacterial endospores in all microbes, and it's sporicidal only in high concentrations. Our hydrogen peroxide is going to also be available in a 35% concentration. At the store, when you buy that stuff on the shelf, like we have pictured in this bottle, that's a 3% concentration. The 35% concentration hydrogen peroxide is scary. I've worked with it a couple times, and it will eat through clothing. It can eat through gloves if you do have the wrong kind of glove on, and it will absolutely burn your skin. It is not appropriate at all in any way, shape, or form for human tissue or tissue that you want to keep alive, but it's excellent for sterilizing inanimate objects. Aldehydes, so groups that have a CHO groups, or molecules that have a CHO functional group sticking off of them, such as glutaraldehyde or formaldehyde, are going to be, generally speaking, very destructive for the cells that you're trying to kill, but are also fairly destructive for the tissues that you may not necessarily want to kill. And then finally we have ethylene oxide gas. Ethylene oxide kills bacterial endospores. It's colorless, and it can exist at room temperature. That's excellent about it. A big downside for it, though, is that it's explosive, and we need to combine it with a lot of carbon dioxide to help minimize its explosive capabilities. And because it can be dispersed through the air in the room, there's a potential chance that you could accidentally inhale ethylene oxide gas. If you inhale ethylene oxide gas, you better believe it's going to cause quite a bit of damage to your respiratory tract. We also have phenol-based compounds, or carbolic acids. These are acidic alcohols. These compounds are effective for destroying viruses, bacteria, and fungi, but not all, just some. Chlorhexidine can destroy most viruses, bacteria, and fungi, and will target bacterial membranes in most situations, allowing for, and then penetrate to the proteins to allow for protein denaturation. Alcohol is going to typically be used at a 70 to 95% concentration on the skin. It's very inexpensive, very non-irritating with minimal use, and evaporates very quickly. This evaporation is going to decrease the effectiveness. You typically need tens of minutes of exposure for disinfecting to occur. And if it evaporates super quickly, it's typically tough to expose the microorganism to it for a period of 10 to 15 minutes. We can use detergents or soaps. These are going to have lots of polar molecules and that act as surfactants. Depending on the detergent, we can have an anionic or a cationic detergent. Our cationic detergents are sometimes referred to as quats, and they are very effective antimicrobials because typically the cell wall of the bacterium has a negative charge. So if we have a positively charged detergent, it's going to preferentially want to stick to that bacterial cell wall. Anionic detergents don't necessarily stick to bacterial cell walls very well, so they don't have as much of effectiveness. Anionic detergents, though, are typically going to be paired with another chemical for sterilization. We'll typically first use a detergent to wash the object and remove the presence of organic matter, and then follow up with an additional method to destroy the bacterial endospores. Chlorhexidine can destroy most bacteria and viruses. Depending on the bacteria, the virus, or fungi, there's a variable amount of effects, though, so it's not very reliable. Oh, I'm getting ahead of myself here. I thought I just talked about chlorhexidine. Here we go, heavy metal compounds. So we can also use heavy metals as a disinfectant. Those could include silver, mercury, or cadmium. Mercury and silver, though, are the ones that are used most frequently, or have been used most frequently. Mercury's fallen out of favor because of its neurotoxicity in human beings. Silver can still be used, although it's typically going to be impregnated into plastics and other solids to inhibit microbial growth on that surface. Mercury, silver, and other heavy metals with +1, +2, or +3 charges are typically going to bind to proteins, functional groups, or active sites of enzymes and deactivate them. So here we have an enzyme. We can deactivate that enzyme with a wide variety of chemicals. Here we have the enzyme in its native state, so it's happy, it's functioning, substrates can get into the active site, so on and so forth. If we expose our chemical to incredibly high heat, let's say in autoclave, we can have complete denaturation occur, so that protein will change shape and no longer function. Or we can have a lower heat that will have partial denaturation, and it's still effective. We change the shape of the protein so it no longer can have the substrate fit in. Or we can block the active site of the protein. Blocking the active site of the protein typically will occur with those heavy metals, or when we have some of our quats or other chemicals that are selectively, preferentially going to bind to those active sites. Here we have a generic structure of a soap or detergent molecule, and we have, here we can see a charged polar group and an uncharged region. All detergents are going to have a charged region and an uncharged region. So here we have an uncharged region. This is going to bind with the hydrophilic regions of the molecules, so the phospholipid head, for example, and this uncharged region can bind with the phospholipid tails of the cell membrane. Here we have a specific detergent, benzalkonium chloride. Benzalkonium chloride has both a charged polar region over here and a non-polar region over here, allowing it to act or function as a detergent molecule. We can also use dyes or pH agents that change the pH, like an acid or an alkali chemical. A dye, generally speaking, is going to be very active against gram-positive bacteria and fungi, because those gram-positive bacteria and fungi are going to have their cell walls directly exposed to the dye. There's very limited application, though, for dyes as an antimicrobial, because they stain and have a very narrow spectrum of activity. They work great against gram-positive bacteria and fungi, but they work very poorly against pretty much everything else. Acids and alkalis, strong or high pHs, can inhibit microbial cells. They have limited applications, though, because they're very corrosive and caustic and hazardous in nature. We can use ammonium hydroxide in detergents and cleaners and deodorizers. This will help our detergents to become more effective. Organic acids, generally speaking, are going to be used in food preservation. As a rule of thumb, if we're working with some kind of a soap or a cleansing agent, it's going to be alkali in nature, and if we're working with something associated with food, it's going to be acidic in nature. So, concept check, class. Which of the following chemicals are considered sterilizing agents? We have A, chlorhexidine, B, hydrogen peroxide, C, alcohol, D, acetic acid, or E, none of the choices above are correct. If you don't know the answer, that is okay. You can pause the video, flip back in your notes, check your PowerPoints, check your textbook, or rewind the video. So pause it and get me an answer. 1, 2, 3, 4, 5. We can see that chlorhexidine, we can see that our iodine-based or halogen compounds are going to be sterilants. We have our chlorhexidine and our hydrogen peroxide and our aldehydes. Aldehydes are disinfectants and sterilants. Alcohol is a sterilant, and heavy metal compounds can be a sterilant. What was not included, though, was acetic acid. Acetic acid is not a sterilant. So the correct answer is A, B, and C. If you have any questions, you can shoot me an email or post them on the discussion board. Happy studies!